Outdoor lighting is something that becomes more challenging with shadow buffers, because if you wanted to do a straightforward parallel projection from sun or moonlight onto your world, you would need a resolution to your shadow map that was large enough to basically cover your entire world, or everything that could be seen on there. And if you chose even a very large value, like a 2000 by 2000 map on there, and you had a decent sized outdoor world area, you would find that the shadows that you'd get from trees and little things protruding up from the ground would be very blurry and fizzly, because there's not enough texture resolution there. There's been some work recently by people exploring perspective shadow mapping, where you try and use a perspective warp to get more detail from a given shadow map resolution where you are. And I don't think that's going to be a really usable solution for games, because there will always be a direction that you can turn into the light where the perspective warping has either very little benefits or even makes it worse, where you wind up with more distorted pixel grain issues on there. So the solution that I'm looking at for outdoor lighting on there is a multi-level sort of cropped mip-maps of shadow buffers on there, where you have your 1K by 1K shadow buffer, which renders only the say the 2000 units nearest you, and it's cropped to exactly cover that area dynamically. And then you go ahead and start scaling by powers of 2 out there till you've covered the entire world, which may require rendering 5 or 6 shadow buffers depending on how big your outdoor area is. But that's really not that big of a deal, and it winds up being like rendering 6 views for for a single point light in an indoor area. And I think that's a pretty solvable problem. So there's a lot of other interesting trade-offs that get made with the shadow buffer approach on there. Like, there's an obvious thought that, well, you'd like to be able to use cube maps for shadow buffering on here. You render your 6 views into the cube map, and then you just sample the cube map. Current hardware doesn't deal with that well, because you wind up you use one of the other texture coordinate values as the compare to value, and you can't directly do it now, although there's some hacks that you can do with referencing a 2D texture and indirecting into, or referencing a cube map that indirects into an unrolled 2D texture. But interestingly, it turns out that that's probably not even what you really want to do, because to do efficient shadow buffers in a real game engine, you need to be changing the resolutions of these shadow maps all the time. You can't just render, if you're seeing 50 lights on there, you really can't render 2K by 2K shadow buffers for everything, especially when a lot of the lights may only be 50 pixels across in their affected area. So what I do is I actually dynamically scale all of the resolutions for every single light that's drawn based upon how big it is in screen, and you can throw other parameters into the heuristic that you use for deciding that. But because of the way I select out the areas that are going to be receiving shadow calculations on there, which I actually use stencil buffer tests, so all the work with stencil buffers and the algorithms for that is still having some payoff in the new engine, even though we're not using that directly for shadowing. But because of the way I select areas of the screen for that, I don't require clamping or even power of 2 texturing on the shadow buffers. So they will smoothly scale from 2000 to 1900, 1800, and so on, rather than making any kind of power of 2 jumps from 2048 to 1024 and various things like that. And it also winds up saving a lot of a really significant amount of memory, because we're looking at large buffers here, where a 2K by 2K one with a 24-bit depth buffer, that's 4 million pixels at 4 bytes each. If you were storing a full cube map on there, that's a good chunk of your video card memory right there. So it actually pays quite a bit to go ahead and render one side at a time, at least on lights that are close up. It is possible that there would be some performance benefits to having all those smaller lights where it doesn't take that much space on there, rendered directly as cube maps. And there's a pretty appalling amount of hardware going into upcoming 3D hardware to allow this single path render into cube maps. I have not been a proponent of this, and I tried hard to get this stuff killed at the last Windows Graphics Summit, but it didn't quite work out, and all the extra stuff went in. And the hardware vendors, I'm sure, will eventually get it all working right, but I question the actual utility of a lot of the geometry processing stuff going in there with replicating all of the viewports and scissors and having basically 6 different rendering views that you're dealing with at a specific time. It was all driven by this thought that we're going to want to render shadow buffers, toss the geometry down one time, and the hardware will spit it all out into the different bins. And it turns out that's really not that important. And when you do that, it winds up having some of these other performance implications where it's not nearly as big of a win as people hoped it would be on there. And even when you do all that, it is a fair amount of hardware cost that's required to implement all of that. So the shadowing is the big question that goes on there. I have it working, looking good. It doesn't handle all the picky cases now. I don't have the outdoor lighting done. I don't have proper individual light specification for exactly how blurry you want the edges to be. And it is worth noting that with shadow buffers, the edge blurring that you get isn't a real shadow, umbra and penumbra. You know, the soft part of a real-world shadow is related to the size of the light emitter, the location of the occluder, and then the location of the surface that it's on. And you get the different effects like the broadening of the soft shadow from the exact point where it intersects the occluder and the surface to a broader one as it goes much further out until eventually small occluders are completely subsumed by a broad extended area light source. And you don't get those exact effects. But again, this has been the standard for many film quality renderings that have been done for years, and it gives the designers the control that they need. They can say, well, this light's going to have a broad angle on it, and we're going to get fuzzier shadows, while this one over here, we have the light extending over such a large area, we're going to tighten it down to reduce the noise, and there will be a little bit of tweaking going on there, and a lot of different parameters. So in some ways, there will be more hacking going on a per light basis than there were with the stencil shadows, because the stencil shadows are what they are. They do the exact pixel same thing, no matter what the geometry is, no matter where the light is, and there will be a lot more kind of judgment calls going on with this. So the other major stuff that's going on will be lots and lots of different surface models. There are some specific things that we'd like to do with adding some things like subsurface scattering to make skin tones look better, partial translucency to let you get the kind of glows through edges of partially translucent things, and through like backlit earlobes, and some things to do better hair and so on like that. I was kind of surprised when I asked Tim what the thing that he would most like improved in the rendering from a game designer standpoint, and the biggest gripe was order-independent translucency, where, again, Doom does not have a proper solution for order-independent translucency. We have basically the same approach that we had in Quake 3, where you can assign sort values to different materials, and it will always sort them. Lower sort values will be drawn before later sort values. And there are situations that fundamentally don't work with that. If you have 2 alpha blended surfaces and you can go to both sides of them, where object A draws in front of object B and then object B draws in front of object A, with the current engine we cannot make that look exactly right. We would have to do something silly like tell where the player is and change out the materials to things with different sort orders. It'll look right from one side, and the other side it'll have this obvious misblend on there. Now, I had a good theory on an attempt to solve this. There's a couple directions that I've got that that are my options for solving this. One path is to go ahead and have separate layer views that, in addition to rendering to your normal direct rendered view on there, you may have the translucency layer, multiple translucency layers, where the engine figures out where they overlap, and if you've got overlapping translucencies, it goes ahead and spawns off another buffer, and then it puts them together as necessary. That still doesn't solve single object or single surface self-intersecting translucency, but that's not a problem that I think is really important to solve. The drawbacks to that would be that it can potentially chew up a lot of video memory. If you run into something where you have 3 translucent planes and it needs to render those out all separately, that could be many, many megs of video memory spent doing that. And that's something that virtualized video memory would help a lot on there, because most of these won't cover the entire screen. But it is an issue. The other thing that sounded like it was going to be a much better direction, and may still be our baseline approach, is to attempt to do all of the translucency in the single frame buffer, but kind of sparsely scatter the pixels that are translucent on there so that they don't interfere completely with the other pixels, and then use post-processing to kind of blend the contributions together. I actually tried some of that early on in Doom, but without the ability to have good post-processing filters on there, it was completely unacceptable. It's just a fizzly mess on there. However, now that we've got the ability to do some broad filtering, and I'm doing a lot of things at the back end with filtering to improve various things, with that, I was able to set up some demos of translucency where the simplest possible case is, say you want a 50% translucent object, you use a separate texture to basically do a stipple test where you only have 50% of the pixels used for that, and they're completely opaque pixels as far as the render is concerned. Half the pixels inside this area have the translucent object, and half of them are just showing through to what's behind it. From a rendering standpoint, this works really nice. You get all the exact lighting and shadowing, and everything works because everything is an opaque surface. And then you go back and have a final pass that renders over the translucent objects and basically blurs together the 4 surrounding pixels there. When you have a fixed pixel grid like that, like this, half of them or every 4th one, and it's on a regular pattern like that, it looks great. It's perfect, perfect translucency, accepting shadows, having the light on it, having the translucency to see behind it, and it works great. The problem is, at that level, we could do an improvement over what we've currently got. If you were able to specify for a given translucent object what its sort of stipple pattern would be, you could then have object A and object B have non-interfering stipple patterns, or only interfering in a particular case, and then you get your order-independent translucency, and that works wonderfully. It's more of a problem when you start wanting arbitrary levels of translucency. Now, you can do that in a dithering operation where if you've got however many, if you're using a 2x2 or a 2x4 kind of dither mask or stipple pattern for this, you can go ahead and have your fixed values on there, and then you can randomly, either statically or randomly, offset the opacity value that you get from either an opacity map, an alpha interpolator, or whatever you're getting from there. And you can blend that all in and randomly pick and choose between these, but that hasn't been completely satisfactory to me so far, where even if I put in a fairly broad filter kernel, if it's randomly picking the different stipple patterns there, it's still a little too visually noisy for me. So I've got a few different levels that I've got on here where the easiest possible thing is if we pick, we can set it up so we can have this randomized stuff, but we have certain good high quality levels, which may be 25%, 50%, 75%, whatever, that look perfect. And then when you're in between interpolating those, you get more and more noise added to it, which is kind of the direction that I'm leaning towards right now, but we'll only be able to see later on when we get more media, how much trouble this is actually going to be. So there's a lot of other interesting graphics technologies that may or may not make it into the next engine. And a lot of things, because we've got the flexible programming interface now, just get tossed in without really affecting the engine. Anything that's a non-interacting surface or that's simply specified with the same environment that we would use for our normal lights, it's easy to just throw in a programmable factor there. The art and craft of engine design is really about what fundamental assumptions are going to be built into the core engine, what's going to be exposed as programmable, programmable features in there, how the workflow, both in the content creation and the utilization of the engine, are done. And there's a lot of things that it's tough to say how important some of these things are. Like internally, there's a number of what I consider flaws with the Doom engine, where, for instance, surface deforms when you have something that's an auto sprite or uses some other deform. That happens in the wrong place of the pipeline to get lit. That's obviously something we want to fix in the next generation, where all geometry gets lit and shadowed exactly correctly across everything. There's some interesting aspects to the fact that I originally wrote the core Doom 3 renderer, which could render pretty much the same pictures that we've got right now. 4 years ago, and I did it in C. It was a fresh start from, I basically took Quake 3 at the time, took out the renderer, wrote a brand new renderer in C, fitting in there and testing it like that. When the whole team started working on Doom, we did make the decision to move everything over to C++. We got everything included, started building the new the new pieces of the code base in there, and all the additional work on the renderer since then has been in C++, but there's still sort of a C legacy to it that the new renderer won't have, where things will always be set up originally where you're communicating with objects rather than passing structures. And I got sort of halfway to actually changing that in Doom, and when you look at the SDK and the headers, you'll see what were going to be nice new class interfaces, but it's still set up right now where you pass handles to render entities and render lights, along with data structures on there, where that really should just be a class on there.